that very generous and kind introduction. And thanks, Peter and you both for inviting me to give a talk. I'm really pleased to see the names of so many old friends and some new friends and people I don't know, but I hope you'll be friendly. So, let's see. There was something I wanted to say by way of introductory remark before I got started, and it has completely slipped my mind. So it'll probably come back to me during the talk, and then I'll interrupt myself sometime in the middle, and it won't be an introductory remark anymore, but it may still be relevant. We'll see. So I'll just jump right in. So let's start with, wait, I'm not on my slides. So I'll be talking today about a kind of model that I have not seen, a model of physical systems that I have not seen discussed in the literature, and that's the introductory remark I wanted to make. The introductory remark is, I'm going to talk about this kind of model that I think is actually quite ubiquitous in physics, but it's one I have not seen discussed in the modeling literature in philosophy. But as I'm sure many of you know even better than I do, the modeling literature in philosophy is just vast. It's enormous, and I have by no means canvassed even a small part of it. So I very easily just may not know there's someone out there talking about something very similar to what I'll be talking about. I just don't know about it. So if one of you does know about it, please let me know. You'd be doing me a great service. So I'll sketch a kind of model that arises in, as I say, I think in all parts of physics. I won't give you. I neither promise nor threaten you with a precise and rigorous definition. I'll sketch it very crudely because it's something that I still can't. I can't give you a precise and rigorous definition of it because I haven't quite worked it out in my own thought yet. I'm still trying to work it out. But I think that the general discussion I'll give, then followed by a detailed example of it, the model we have a black hole, one model at least, we have a black hole evaporation. I hope will clarify what I'm talking about. And then I'll conclude with some very general and rather probably somewhat sanctimonious and self-righteous, preachy remarks about understanding and realism. So for those of you who are waiting for the more inflammatory parts of the talk, that's where that will come in. So I'll begin with a quote by a recent paper by Lydia Patton. She says, just to set the mood, the structuralist, structural realist, and methodological realist accounts all rely on one thing: a history of successful scientific theories in which not only posits about entities, but also formal elements like variables and relations are indispensable instruments. I want to begin by raising the question, what happens then if precisely the problem that faces scientists is the inability to solve the equations, the inadequacy of our current theory to provide a model of a given domain in which the results we can prove in that domain can be represented as consequences of a deductive axiomatic system? What happens if a scientific theory is successful, but not in the sense that the equations of the theory allow it to be represented explicitly as a deductively complete and categorical system? Now, as it happens, this is, I think, the human condition, or if one likes, it's life in the big theoretical city. For every theory we have, we know almost nothing about the nature of generic solutions to the equations of motion, the field equations. What I mean by that is, we know very few individual models, and generics. We know almost nothing about individual models that we have no idea how to construct in any way graspable by the human mind, or indeed even how to identify it if one bit us on the ass. Think about general relativity. There's a sense in which every single Lorentzian four manifold is a solution to the Einstein field equation. You give me the metric, I'll compute the Einstein tensor, and I just set that equal to 8 pi times. I define the stress energy tensor by 8 pi times, well, 1 over 8 pi times that. Solution to the Einstein field equation. But clearly, if you think about the extraordinary, the mind-boggling possible complexity of the topology of a four manifold, and the wild inhomogeneity possible for just a generic, two-index symmetric, non-degenerate tensor field on that manifold, it's almost it becomes quite clear on minimal reflection that we know almost less than measure zero of individual solutions, the Einstein field equation. If one holds, and just as a side remark, I can't resist pointing out, if one holds that a theory is characterized in a strong sense by its family of models, where that often means in the philosophy of science literatures something like individual solutions to equations of motion, then the overwhelming majority of the content of the theory is something that we do not know, are in fact nowhere near knowing, and have good reason to think we will never know in anything resembling thoroughness and detail. Epistemologically speaking, to postulate the very idea of a theory as a well-defined structure in this sense is an act of faith. I really like that phrase, epistemologically speaking, it's an act of faith. And I can't claim credit for it. I actually got that from Kareem Tebel, to give credit where credit is due. But what I'm saying here isn't just true of general relativity. It really is true of, I mean, think of a theory that is prima facie as simple as Newtonian gravitational theory. I think we tend to think it's simple because we almost never think beyond the two-body problem or the three-body problem under extremely restricted conditions. But if you just think about the 358,246 body problem, well, obviously we have no way of knowing anything about solutions to that. And that's, 348,560 is a relatively small number in the world of n. We really know almost nothing about generic solutions to the equations of every theory that we know. So what to do then when you can't solve equations and either other mathematical difficulties prohibit approximative methods and numerical simulation, because that is the strategy that philosophers of science have focused on. We can't solve this equation under these conditions, so let's try and construct an approximate solution, or let's try and numerically simulate a solution. But it often happens, in fact, that the equations are so difficult, or the conditions we want to study are themselves, for some reason, present some difficulty, that even approximate solutions and numerical simulations are difficult, if not impossible. And that does happen even in classical general relativity and certainly in semi-classical gravity. So that's one possibility that you can't solve the equations, and approximate methods and numerical simulations are, for whatever reason, not feasible. Another possibility is that one can, in fact, solve the equations to some degree, perhaps, but only, but one doesn't want detailed information about the individual models or individual possible solutions that we do know about, because, for instance, the only ones we can derive are trivial in one way or another, as is very often the case in GR and semi-classical gravity, and narrow classes of solutions that we may also be able to characterize with some exactitude, say the ones depending on exact symmetries and or the ones available only in 2 dimensions or something like that. Other wild idealizations just won't do the job. And of course, this problem becomes even more acute when it is difficult, if not impossible, to experimentally access the regimes in which one expects the behavior of interest to manifest itself, again, as in the case of GR and semi-classical gravity. Well, what physicists find themselves, mathematical, theoretical, experimental physicists find themselves in this situation all the time. What do? They're not hopeless. What they do, one thing they do, is they try to prove what, for lack of a better word, I'll call general results. But what exactly is it that one is then doing in proving general results? Well, one thing that falls under this rubric is proving something like theorems. The one either is setting up a disjunction for the next slide. So the theorems are one possibility for what I mean by general result. Something else will come on the next slide, which is the other thing that comes under the general rubric of a general result. So the first thing one can try is to assume something of a suitably generic character, for instance, an energy condition in general relativity, and then try to derive or argue for something of a suitably generic character. A result often, but not always, of the form of a reverse theorem. And there are various kinds of theorem-like results that one can try to prove under these when one is in this situation. There are non-existence claims, for instance, that there are no non-singular cosmological models under suitably generic conditions, or rigidity stability claims that that are rigidity and stability in topological sense. There are past singular closed cosmological models satisfying the strong energy condition are stable. There are scarcity genericity claims in a measure theoretic sense. So, cosmological models of the killing field are scarce. There are non-constructive existence claims like the classic singularity theorems. There are non-constructive behavioral claims, formation of closed trap surfaces under gravitational collapse. So that's one thing that physicists do. I'm not going to focus on that, although it is, I think, a practice in physics, a methodology in physics that philosophers have not attended to enough. But I'm rather going to focus on another kind of general result that physicists try to construct under these situations. And for lack of a better word, I'm going to call it a principal model. I don't like this terminology for several reasons, but I'm really bad at naming things. So if after the discussion, if anyone has any suggestions for a better name, I would definitely love to hear them. And it has nothing to do with the classic principal versus constructive theory distinction. I call it a principal model because it's a model that you construct based on general principles. And very crudely speaking, what you do is you fix some general principles and generic conditions, for instance, the framework of semi-classical gravity. You then characterize general structures that embody the principles and conform to the conditions, a particular quantum field satisfying the semi-classical Einstein field equation on an asymptotically flat black hole space-time, or not a particular one, but some species of a quantum field. And you derive a statement about generic features of the character and behavior of these general structures, the Hawking effect, black holes evaporate. So why am I saying that this is not in some sense a solution to the equations of motion or approximation to a solution to the equations of motion or a simulation or something else that has been well studied in philosophy? Well, let me try to explain. So these models often involve behavioral claims. They are not individual solutions to equations of motion or field equations. I'll work through the example of black hole evaporation in some detail because this is that example very clearly exemplifies all of these claims I'm going to be making. One doesn't get an individual solution to the equations of motion or the field equations by this generic argument. This argument that one constructs based on the assumption of general principles and generic conditions. Usually, in fact, no exact individual solutions are known that represent anything like such systems, especially not in the generality postulated. They do not otherwise represent individual systems in any straightforward sense that I know of. Sometimes they are not grounded in exact, rigorous general results. That's certainly the case with general models of black hole evaporation. They're not approximations to or idealizations of solutions. We don't know any solutions to approximate or idealize. And quite generally speaking, there are no clearly specifiable families of solutions that we know of that they correspond to. And again, this will come out very clearly in the discussion of black hole evaporation. So that's why these are models in some sense of the behavior of a physical system, but they are not models in any sense that I'm familiar with in the scientific or philosophical literature. They rather represent general features that we expect certain, often loosely characterized, merely postulated families of solutions to have. Almost always one can loosely characterize such postulated families in several different, often mutually contradictory ways. And thus they have, for lack of a better word, an interpretive looseness and a flexibility of consequence to them that's not characteristic of exact or approximative solutions. Again, this will come out very clearly in the case of black hole evaporation, when the flexibility of consequence is so great that one, in fact, when one tries to make the principal model more specific and narrow it down so that it becomes more concrete, so to speak, one finds that one can do it in a number of, in fact, mutually inconsistent ways, each of which each of which nonetheless still clearly conforms to the general pattern that the principal model presents to us. So let's in fact work through this example to see, both because it's of intrinsic interest, the physics itself is of intrinsic interest, and it also will illustrate, I hope, quite clearly what I'm gesturing at with this idea of a principal model. And I hope that in turn, the discussing, elucidating our understanding of black hole evaporation using this idea of a principal model, I hope will shed some light on what exactly it is that we can understand about the physics of these systems when we argue about them in the way that we actually are arguing about them. So as I've already said, black hole evaporation by the Hawking process and semi-classical gravity, I think, is a beautiful example of the kind of thing I'm talking about. I do want to emphasize, though, that again, this is not these principal models are not at all restricted to general relativity or semi-classical gravity. The same kinds of the same kinds of theoretical practice and methodology is used ubiquitously all over physics. It's used in attempts to discuss general properties of solutions to the Navier-Stokes equations. It's used in Boltzmannian and Gibbsian statistical mechanics to try to characterize generic behavior of generic probability distributions that govern the macroscopic behavior of the statistical system. It's ubiquitous in Lagrangian quantum field theory. It's all over physics. So there are no exact solutions of the semi-classical Einstein field equation known for a space-time representing an evaporating black hole. Well, there are some in 2 dimensions, but 2 dimensions, who cares? There are no 4-dimensional solutions. Let's say that. Just because I know some smart aleck is going to interrupt or ask a question, but what about the 2-dimensional solutions? Who cares? I'm talking about possible models that apply to something in our action in the world. So there are no exact solutions of the semi-classical Einstein field equation known for a space-time representing an evaporating black hole. And the approximate ones we have are severely limited in their scope and their potential to yield general insight by dint of various kinds of almost absurdly idealizing assumptions. Well, for instance, the 2-dimensional space-time, but also you'll see. It would take me too long to go into the details, and I'm gonna struggle to make this talk fit in the allotted time anyway. So let me just make the general claim, and if you have questions about what the absurdly idealizing assumptions are, you can ask me during Q&A. So here is what happens in a typical argument for black hole evaporation in deriving the principal model, what I'm calling the principal model of black hole evaporation. One makes some topological assumptions, say the domain of outer communication is simply connected. That's something that that is an assumption one can in fact make mathematically rigorous and precise. One generally makes some causal assumptions, no closed timeline curves. Again, an assumption one can state with mathematical precision. One makes some stability assumptions, small perturbations do not destroy the event horizon. This is something that in fact sounds like it might be exact and rigorous, but it's not. We don't have a completely general result of this effect. And it's very difficult to make sense of, it's very difficult to state precisely what one means by small perturbations. So this is kind of a rough and ready and quasi-heuristic assumption. We make assumptions about asymptotic behavior and structure, about the existence of certain kinds of instantaneous symmetries on space-like slices at infinity, about almost conserved quantities, because of course there aren't going to be exactly conserved quantities because the black hole space-time isn't perfectly stationary. We make assumption that their energy flux is at null infinity, but they don't contribute to curvature. You know, there's the Hawking radiation flux, but we're going to assume that the spacetime is asymptotically flat. So there's a whole bunch of rather complex and subtle assumptions that one makes that are hard to make exactly rigorous and precise, especially given that the energy flux at infinity is supposed to be test. It doesn't contribute to curvature. But of course, if the black hole is going to evaporate, then the quantum field near the horizon can't be test. It must couple with curvature by way of the semi-classical Einstein field equation, or else you're not going to get evaporation. You know? So there is some mild tension that it is at least prima facie difficult to resolve with any kind of technical clarity or rigor. Nonetheless, the conceptual structure of what one is assuming is, I think, fairly clear. There are behavioral assumptions then about the coupling of the metric and the matter field near the horizon, and you know, it's almost stationary in some sense. Again, that is very difficult to make precise. It's adiabatic in a sense that one can gesture at and make somewhat precise. And then there are some further technical arguments, assumptions about, say, the singularity structure of the expectation value of their normalized stress energy tensor operator for the given kind of quantum field near the event horizon. And one can go on and on and on. The point I want to make is that the kinds of assumptions one makes are a very funny mixture of very, very crisp, rigorous, precise mathematical statements, kind of quasi-rigorous mathematical statements, ones that you can kind of make precise if you squint your eyes, but it seem to have pretty clear physical content. And then ones that you really can't make precise at all, but have very clear physical content and are really important to making the argument. And then you put this mash, the sparago of assumptions together, you make a rather complex and largely heuristic argument based on, again, some more rather subtle assumptions that relate the quasi-local intra-spacetime behavior, the behavior near the event horizon, relating that to global asymptotic behavior out near null infinity, and you come to your conclusion. Local negative energy fluxes associated with a positive thermal Hawking flux decrease the global ADM mass, which in turn decreases the area of the event horizon. Radiating black holes evaporate. Now, Hawking, to his great credit, in the seminal 1975 paper in which he first gave the detailed calculation for Hawking radiation, and also gave the first argument that this Hawking radiation would in fact cause black holes to evaporate, would cause black holes to shrink. This is how he himself, I think he very clearly recognized the kind of argument he was making. I think he very clearly recognized what he was up to. So this is a quote from that article. It should be emphasized that these pictures of the mechanism responsible for the thermal emission and area decrease are heuristic only and should not be taken too literally. It should not be thought unreasonable that a black hole, which is an excited state of the gravitational field, should decay quantum mechanically, and that because of quantum fluctuation of the metric, energy should be able to tunnel out of the potential realm of a black hole. Physicists aren't always incredibly careful about the words they use. Physicists tend to be much less careful writers than philosophers tend to be as readers. I actually got into a really funny argument with Carlo Rovelli once about that. Put that aside. So I can't be positive that Hawking, quite self-consciously used the word picture here in a sense that I want to attribute to him, but it at least serves my purposes. It's felicitous that he used this word. I like to think he used it self-consciously. That's exactly what his argument, if you're familiar with the paper, that's exactly what his argument for evaporation was. It's a picture. It is not a rigorous calculation. He's not giving anything like a solution to the semi-classical Einstein field equation. He's not showing in any detail how the stress energy content of the quantum field really couples with the classical curvature. He is assuming some general principles about energy conservation, of the kind that I listed, and is concluding, well, there's energy going, there's stuff falling into the black hole, there's stuff escaping to infinity. On balance, it looks like the black hole is losing mass, its area should be shrinking, it looks like the black hole's evaporating. somewhat crude, but not, I think, inaccurate summary of what he was up to and what many arguments that that conclude that black holes evaporate are what form they have. What I was calling the interpretive looseness and the flexibility of consequence as a general feature of principal models is that I hope it's somewhat more clear, given this example that I've discussed, that what I mean by interpretive looseness and flexibility of consequence is in part, at least in part, captured by the fact that the principal model does not pick out a unique behavior, nor a unique individual system, nor even a unique individual kind of system. It is rather schematic in a way that is very open-ended. And just to give you, to make concrete this idea of how open-ended these models are, I will show you 3 pictures from the 1984 paper by Bob Wald, in which he states and proves the most general version of what I think is now called the Kodama-Garroch-Wald theorem about the causal structure of an evaporating black hole spacetime. And these 3 pictures will show you that the argument that was given for black hole evaporation, which is the argument, the kind of argument that Wald relies on in this paper, and the conclusion that this argument leads to, allows one to fill in the details in ways that are mutually contradictory and yet still very clearly conform to the spirit of the principal model, of the general schematic model. So first, this is a picture of, this is a space-time diagram, not a Penrose-Carter diagram, of the kind of quasi-local interior of the evaporating black hole spacetime. What looks like the cone of a rocket head is a collapsing, a ball of matter, say a star or something. What looks like the nib of a fountain pen, or perhaps a spearhead, is the event horizon. The little squiggly line going upward, as always, is the singularity, and the wavy lines going diagonally upwards are the Hawking radiation. And pretty much all, and what of course happens at the tip of the spearhead, at the tip of the fountain pen nib, where the singularity ends, is of course a matter of great debate. Now, at least in 1984, when Wald wrote this article, everyone, I think, pretty much would have agreed on at least this part of the principal model, what is illustrated by this diagram. Of course, now there's the firewall debate, so not everyone would even agree on this picture. But at least back then, and I think that I really don't know where people stand on firewalls these days. My sense is that most people still reject firewalls. But be that as it may, there's still at least a sizable percentage of the population of theoretical physicists who think about these things who would agree that this is crudely accurate for the interior of the evaporating black hole spacetime. So far, so good. But if we want to look at the global structure of the evaporating black hole spacetime, one that is completely consistent with the argument that led to the conclusion, well, this is one possibility. So this is now a Penrose-Carter diagram. And what happens here is that what this diagram is illustrating is that the little dotted narrow half ellipse sticking that way in the middle of space-time is a region in which quantum gravity effects take over, so to speak. We don't exactly know what happens there. And But what we do know is that the classical description of space-time breaks down in some way or other. Perhaps a singularity is avoided. But in any event, no matter how exactly it is one thinks this may happen, the information that falls into the black hole is nonetheless released and escapes. So this is completely compatible with the argument that led to the conclusion that black holes evaporate. But there's another possible picture, one that is probably more familiar to most of you. This is what one may call the standard picture of black hole evaporation, at least among people who were trained in the relativity tradition. I don't think a string theorist would like this picture. Here, there is no information escape. The black hole completely evaporates. At the point of evaporation, the singularity is, in some sense or other, nakedly visible, whatever exactly that means. This global structure is also completely consistent with the argument and conclusion of the principal model. So, given what I've sketched about the character of principal models and what we've seen about how they work in the specific example of black hole evaporation, in particular, what I've called their interpretive flexibility and their interpretive looseness, I guess, and flexibility of consequence. That was the phrase I used. What is their epistemic value? What, if anything, understanding can they give us? And I'll conclude by making a few rather tendentious remarks about what they may suggest for traditional approaches and popular contemporary approaches to realism, harking back to the quote I started the talk with from Lydia Patton. So what can we learn from these kinds of models, and what can we do with them? Well, I mean, of course, it depends on the character and the epistemic warrant of the general principles and conditions we've assumed in the construction of the model in the first place. But we can say still, I think, a few general things that are at least suggestive. So first of all, what are they useful for? Well, they're useful when we have general behavioral claims that we want to study or think about that cannot easily be captured by theorems. Cosmic censorship is a great example of this. The current kind of a schematic statement of strong cosmic censorship is something like the following. The maximal globally hyperbolic future developments of generic physically reasonable initial data are future inextendable to regular Lorentzian manifolds. Now that may sound like it's a fairly precise mathematical statement, but it's not. Particularly the words generic, physically reasonable, and inextendable and regular all have to be made precise. And it's very difficult to, in some cases, it's very difficult to do it at all. In other cases, there are many possible ways one can do it with no a priori way of figuring out which one is preferred for one reason or another. So in this case, in these kinds of cases, it can be useful to study, argue in the way that I've suggested principal models allow one to, rather than necessarily trying to construct an exact theorem and trying to prove an exact theorem. Of course, the goal is almost certainly then to construct and prove such an exact theorem. But how one gets there, I think, very often goes by way of arguments of the type of principle that principal models allow one. It's also the case sometimes that principal models are useful when, in fact, we do have exact theorems and we have proofs. I mean, in the sense that we have a mathematically rigorous statement that we have a real proof of. but they are technically abstruse and really have no perspicuous physical interpretation. And so the general behavioral claim, radiating black holes evaporate in a weakly predictable way, but not retrodictably, are, or at least can be, epistemically more valuable for the purposes of further exploratory investigation than the technically secure result. Let MGAB be a time-orientable space-time, and let sigma 1 and sigma 2 and it be closed acoronal sets, such that sigma 1 is connected and sigma 2 is edgeless. Suppose there's just a point in the domain, in the future domain of dependence of sigma 1, such that P is not in the union of the chronological past of sigma 2 and the causal past of sigma 2 and the causal future of sigma 1. Suppose further that the set K, defined by the set 1 with the intersection of the past domain of dependence of sigma 2 with sigma 1 removed, has the property that the causal future of K intersect with sigma 2 has compact closure. Then sigma 2 cannot be contained in the future domain of dependence of sigma 1. Now, I read that out because just to derive home what a mouthful that is and what a headful that is. You know, even cognoscenti, it takes even cognoscenti a minute to get their heads around that and figure out what the hell is going on. And of course, it's a beautiful theorem, this the Kodama-Grosjean theorem. It's a beautiful theorem, but it really does takes some real thought to figure out exactly what the physical content of it is. And once one has the physical content in mind, one uses that crude picture of the physical content, the evaporating black hole picture in the principal model sense, really to, in exploration, before one goes back and tries to make one's arguments rigorous, if that is in fact what one really cares about anyway. Sometimes you don't care about making things perfectly rigorous, you just want to make some heuristic progress. And it's especially true that it's useful to do this when the general behavioral claims that one is interested in, radiating black holes evaporate in a weakly predictable way, but not retrodictably, go beyond strict interpretations of the technical results. And by that I mean, and this is the case here, in order to turn the mathematical statement of the Kodama-Grosjean theorem into something with a real physical content that is applicable to the picture of evaporating black holes that we want to work with, that we think has some theoretical validity, we have to make assumptions that are not rigorously formalizable in our current state of knowledge. For instance, about the character of the propagation of quantum fields in a curved space-time and how they couple to the metric. We can't solve that equation exactly. So in order to interpret the Kodama-Grosjean theorem in a physical sense, we have to go, we can't just give a physical meaning to each mathematical symbol that occurs in the theorem. We have to go far beyond what actually appears in the theorem. Quantum fields, for instance, don't even appear in the theorem. But if we want to talk about evaporating black holes, we have to have a physical picture of how the quantum fields are propagating on this classical spacetime and coupling with the curvature. The theorem doesn't tell us that. So principal models does seem to give us understanding in some sense, but what sense is that? And what can we not learn from them? Well, again, semi-classical gravity is a fascinating case. It's one of the reasons why I'm discussing it today. Not the only reason, because again, I think the physics, it's the theoretical possible physics itself is of great intrinsic interest. But this is a case in which general results and principal models seem to be perhaps not the only way, but almost the only way we have to proceed, given the manifest technical difficulty of and deep conceptual and physical problems involved in trying to combine GR and QFT, especially with regard to the divergences and other pathologies accruing to solutions of the semi-classical Einstein field equation. One thing we cannot learn from these models, say a black hole evaporation, one thing we cannot learn from models alone is which, if any, of the compatible families of more exact models are the right ones. So is it the first Penrose-Carter diagram I showed you from the wallpaper, or the second Carter-Penrose diagram I showed you? Or and those don't exhaust the possibilities. There are yet other ways of making the black hole evaporation model more precise and more concrete that are themselves inconsistent with those two ways of doing it. And in this case, in particular, in the absence of experimental probing, what we cannot learn is whether there is any unimpeachable veracity to the results in models, whether there are any systems that behave in any way consistent with the model in the real world. But we can, I think, still have some weak confidence that we are on the right track, given our epistemic attachment to the general principles, local validity of QFT and curved space-time, and to the reasonability of the generic conditions, say, no causal pathology and all those other assumptions we made, that we used in constructing the principal models, and because of our epistemic faith in the plausibility of how we combine them in semi-classical Einstein field equation. We can also gain some warrant from forms of consilience and robustness analysis. We have derivations of the same model, same principal model, the same picture of black hole evaporation from different assumptions and from, loosely speaking, perturbations of the same assumptions. So understanding in this sense then does not seem to have anything to do with gaining knowledge about fixed classes of real physical systems, because we don't yet have, the principal model by itself doesn't unambiguously pick out a unique family of physical systems it applies to. It is the kind of knowledge and understanding it gives us is of a much more pragmatic, methodological kind. It's something like the capacity to operate successfully in a scientific enterprise in all its aspects and parts, to use our representations and instruments as the basis for the fruitful continuation of the enterprise, as part of evidential warranted testing, as basis for predictions and characterizations, as inspiration for potentially fruitful new investigations, as the grounds for conceptual clarification and innovation in foundational work. And perhaps most of all, to grasp how our representations and our instruments relate to, inform, and substantively contribute to the constitution of each other, and to grasp that in such a way that it founds the work successfully continuing the enterprise. I think that these principal models also can give us some insight into the epistemology and general structure of scientific knowledge. And these are obviously extremely programmatic and general hand-waving, broad brush remarks. And yet I think they still are nonetheless important to make. One of the things I find most fascinating about these models is that the nature of the representation of physical systems is not straightforward. They don't represent individual systems as I've, in any straightforward sense that I know of, at least as discussed in the philosophy literature. They don't represent well-defined classes of systems. So what do they represent and how? I myself am tempted to say they don't represent in any traditional sense, that they don't represent anything in any traditional sense, though. And it's one way to see this is that, for instance, it's difficult to make sense of what these things can teach us if one is using something like the semantic view of theories to understand how it is that theories acquire empirical content. Because in this case, the whole point is that we don't have access to any individual models or exact models. We don't even know whether there are any individual models or exact models that really conform to the general picture that the principal model is giving us. So inter alia, we cannot characterize their empirical content or judge their empirical adequacy using any of the tools that the semantic view provides. And just as an aside, I can never resist beating up on the semantic view whenever I have the chance. The kinds of rigidity and stability claims that are often an important part of principal models are relations among individual models, among individual solutions. And the semantic view, with its Tarski-like semantics, is just ill-equipped to handle that kind of knowledge claim. The principal models, because of their often very heuristic argumentative structure, I think they're also useful in highlighting the ineliminable role of pragmatic factors in so much of physical theorizing. Often, if not always, I think the general state of the entire epistemic community bears on whether one is justified in accepting a principal model and using it as the ground for further argument, explanation, or prediction in a way that one has grounds for believing has at least prima facie epistemic warrant. What, for instance, widely accepted standards of heuristic argument with regard to a particular theory, for example, constrains what can legitimately be thought of as a prediction of the theory. And these can and do change over time. There was, when Hawking first published these arguments in 75, and even before that, he distributed copies of the manuscript to informally to some people. I think in late 74. He had a lot of pushback. People were very skeptical of the kinds of heuristic argument he was making. But very quickly, he won the community over. The people very quickly accepted that the kinds of heuristic argument he was making were epistemically reliable in some sense. How exactly that transformation happens, I think that's someone who. I think it's a fascinating question, but I don't have the historiographical or sociological tools I think required to really give a proper discussion of that. I wish someone would. I think it's fascinating to try to figure out what happened in 75, 76 that all of a sudden made everyone think these were great arguments. So whatever understanding the principal model does give us, it is not understanding that can be used as evidential warrant for the theory in any straightforward traditional sense. For we cannot test the truth of the general propositions that seem to be that we want to associate with the principal model. Only corroborate them in special cases, and often we cannot even do that. I mean, think about the singularity theorems of GR. We'll probably never be able to test those, sadly. But it's important to recognize that what I'm pointing to here is not anything like the problem of induction in any traditional sense. It's rather the fact that we don't know with any exactitude what the general case is here. Or to put it another way, the general propositions one wants to test the truth of, well, they're not univocally picked out by the principal model. There are many mutually inconsistent general propositions one can derive from the principal model that one might want to try to test the truth of. I also don't see any sense in which it is fruitful to conceive of these as fictions, whether felicitous or not. That's a whole other long argument. Okay, so I'll just make that tendentious remark in passing and see whether there's any pushback on it. But neither is there any clear sense in which they may be or not approximately true. I don't know what the quantifiable measure of approximation for general behavioral claims is or can be. And I mean, finding one or a dozen or a million systems that in some sense behave approximately like that schematized by the principal model would not show that the principal model captures something approximately true about the world in any representational sense anyway. Only about the application of general principles and generic conditions to those kinds of systems. So to conclude with I'll say that principal models seem to go far beyond the tools used for prediction of the shallow instrumentalist. Now I'm harking back to the passage I quoted from Lydia's paper at the very beginning of the talk, when she was talking about what tools the realist standardly relies upon. But the principal models also fall far short of the representational needs of the naive realist. They rather give us, I think, understanding characterized by a fruitfulness of conception, and this is a pragmatic virtue. And I mean that in the sense of a Peircean kind of pragmatism. So I will actually conclude with a valediction in the spirit of Kierkegaard and Howard Stein following Patton's pregnant remarks. And I don't claim to have given an argument for anything I'm about to say. Just when one thinks about how physicists actually proceed in trying to learn about and understand the world, this, I think, is a picture that very naturally falls out and makes sense of what it is physicists are doing and what kind of knowledge they have in a way that I find both realism and instrumentalism to be incapable of giving with a similar richness. Realism is not a proposition whose truth value can be affirmed. It is a way of thinking, an attitude, a style of moving forward in one's cognitive work, shaping and informing but not contributing to the content of one's thought. It is a leap of the absurd into faith, but at the same time a sober reflection that is only one step in the ongoing dialectical dance of one's cognitive capacities in their attempt to explore the world. Itself to be given over to instrumentalism, also a leap of the absurd, as the times demand. And that will give over in its turn back to realism and the bacchanalic comedy of thought, which from time to time settles down in its stately progression of the tragedy of understanding and back again and again, eventuating, I hope, in the pragmatic attitude. And so one is a realist and one regrets it. One is an instrumentalist and one regrets it. One is a pragmatist and learns to take joy in passing from one regret to the other. Thank you.
Okay, well, that was a beautiful, beautiful talk. Thank you so much, Erik, for this inspiring lecture. I think we will do the usual system of a raised hand system. Now, before we do so, oh, there's a comment from Brian Roberts to everyone. I'll read it out. Thanks for the lovely talk and the apparently poetic conclusion, which seems to also contain the spirit of author-binding. You suggest that this principal model is both successful but not obviously truth-conducive, so rejecting the typical realist purported relationship between success and truth. But how then do you explain the success, and does this really deserve to be called success? So that's from Brian. Erik, why don't you handle this, and then we'll have three raised hands: Peter, Carl, and Jacob.
Okay, so I would say, Brian, that starting with Brian's remark, with Brian's question. I am not claiming that the principal models are not truth conducive. I am claiming that they're not truth conducive in any way that can be captured by standard ideas of representation and the ways understood in the standard realism instrumentalism debate. So I myself am a pragmatist, and I think that there are very good ways of making sense of some proposition or other kind of general cognitive structure being truth conducive, or proposition can be truth conducive. You know what I mean? Something's being truth conducive without relying on a picture of kind of representational verisimilitude. Rather, being truth conducive means being conducing to success in the further continuation of scientific enterprise. That is obviously a very shallow thing to say. I would have to say quite a lot to make that more substantive and more precise. I think that it's possible to do, but okay, I'll leave it there.
So Peter, I think, had his hand. Why don't we?
Thank you very much for the talk, Erik. Much to discuss and think about. I want to focus on what seems to me a very interesting way one could connect this with a concept that you mentioned somewhat in passing towards the end, which is the idea of the heuristic. And it seems to me that, when I think about the 4 Einstein papers of 1905, although it's often ranked second, the photon paper, the quantum of light paper, is in many ways the methodological radical move that Einstein makes in this period, in saying that he treats the photon, although this new quantum of light, in a way that doesn't know how to finish the story it begins, in a way. This is going to help us understand a variety of phenomena, allow us to connect ideas of statistical mechanics with electrodynamics, allow us to think about particular experimental phenomena, only one of which is the ejection of electrons from a surface and the photoelectric effect, but a variety of others as well. But that this concept, this idea, which really is somewhat new in the way he's prosecuted it and the depth he's prosecuting it with in this time, allowed us to open up and advance our understanding and unification of different domains of knowledge, even though the story is not complete. It cannot fulfill the obligation. And as such, it made other people crazy. I mean, Poincaré said, you know, you're saying this light is a particle and not a particle. From a contradiction, everything follows. And, you know, reacted quite violently when in the one moment where we know he and Einstein interacted at a meeting. So I think that it was a tolerance for the ability to handle conflicting notions in the notion of a heuristic assumption here, or a heuristic move, that in a way I would think of your idea of a principal theory is an extension of the heuristic, which is more restricted in its remit, but you know, now connected with a more elaborate, you know, a more elaborated logical structural development, whether it's diagrammatic, as in the example that you gave, or otherwise. But it's saying, you know, here we can go, but perhaps at this moment not farther, but it will help us advance. It emphasizes the downstream implications, whether prediction or opening up of new forms of inquiry. It seemed to me, in the spirit of a heuristic, more elaborated, given more structure, associated in the instance you gave with the diagrammatic, but has that same hopeful, pragmatic attitude of advancing and, in a sense, refusing to say more than it's warranted for us to say at this time.
So, Peter, thank you for that. I completely agree. I think what you said is entirely grist for my mill. I think it's a beautiful, what you laid out the example very beautifully, and itself is a beautiful example of exactly the kind of thing that I'm trying to get at. I agree in this talk in a more restricted, semi-formalized kind of way. I think that one I hadn't thought about the 1905 paper. I'm glad I certainly will. I mean, you and Porter and others here know more about this history than I do. But one thing that it does bring to mind that did occur to me while I've been thinking about these things is the Bohr atom of the model, which of course is directly dependent on the Einstein 1905 arguments, and how one might consider the Bohr atom, the Bohr model of the atom, as a principal model, especially insofar as it contains some people have claimed self-contradictory elements, just like the Einstein 1905 paper. So I guess I can say, in sum, I pretty much agree with everything you said. You summed it up more beautifully than I could have. Thank you.
All right. I see that Carl has a raised hand.
Yeah, thanks, Eric. That was fun. Peter had heuristics brought to mind by your talk and the discussion of the black hole evaporation model. But a different thing happened to me. What your summary with Hawking's remark of the black hole evaporation model brought to my mind was a causal mechanism, or a model of a causal mechanism. And that seems to me like a nice way to talk about what Hawking gives us. And he uses the word picture, and that's the way mechanisms are often presented to us, precisely as with pictures and arrows, and you can see how the various parts work together to lead to a certain conclusion, even though you're not giving a faithful description of any of those parts, or even very often of their interactions in any exact sense. And so with that idea in mind, for at least for the black hole evaporation, it seems to me that there is a sense in which we can say that the evaporation model gives us something that's approximately true, namely that it depicts the causal mechanism correctly in a structural sense. It gives us the structure of the causal mechanism by which black holes evaporate, and that may be a very limited, but it's still a way in which you can talk about giving us literal approximate truth.
So I like the general suggestion of thinking about of at least in this case being able to interpret it in this mechanistic a mechanistic causal network kind of way. I'm not opposed to that at all. Where I would push back is on the idea that insofar as one does want to construe this kind of what I'm calling a principal model, at least in this case, as giving us something like a picture of a causal mechanism, I would, putting aside my own personal qualms about causal talk in physics, I'm often quite leery of that. But put that aside for the sake of argument. Let me grant you that's relatively unproblematic. Then I would still say that that the picture that this argument is giving us, the picture of a causal mechanism this is giving us, is I'm happy to grant that it is in some sense that we can have in some kind of epistemic faith or epistemic, we have some kind of warrant for having confidence that we're on the right track, that this is the right kind of mechanism. But it's so underspecified that I still am this is where I want to push back. It's so underspecified that I simply don't know how to understand it as representational in any of the standard senses that are used in the debates about representation and realism. It can, and precisely because it can be fleshed out in so many different, made more precise and concrete in so many different mutually inconsistent ways, that I don't understand how to say that it really is, it represents in any standard sense. So this is, I think, maybe a continuation of my brief answer to Brian's question. I certainly want to be able to talk about these models being successful, these models being truth conducive in some sense. I don't know how to think about that in anything like a standard, in any of the standard senses that debates about representation turn on or rely on. So.
Okay. Thanks. I mean, I could push back, but we probably have more questions to get through.
I normally keep quiet, mostly because I'm the host, but on a topic so close to my heart, and on an example, sorry?
I definitely want to hear what you have to say.
Yeah, on an example so close to my heart and something I've actually worked on, I want to say, or I want to ask you the following. So, I'm totally receptive and sensitive to everything that you've said. However, what strikes to me as just a kind of slow and obvious way to deal with your concerns is to say, well, when you come up with a theorem, when you use a theorem as a part of some reasoning, as a part of an argument, as a way to talk about a particular scenario, you should seek to formulate your theorem in a way that suggests different levels of robustness that go into the assumptions of your theorem. I'll give you a quick example. Let me first and foremost assume that I can model my space-time, for instance, to take general relativity as an example, as a Lorentzian manifold, right? That will be my kind of very robust assumption one. And then I should seek to prove theorems that have this kind of stratified kind of robustness, where I can see which assumptions kind of build on each other, which are the ones that I'm most likely to eliminate or question. So with that remark given, let's go back to Gaurosh-Kodama-Wald. So as you know, Erik, I actually studied that theorem and proved two theorems which kind of supersede that theorem in a kind of very clear way. In particular, the main theorem that I prove in my paper from 2 years ago now is one where the key assumption, unlike the Gaurosh-Wald-Kodama, where you've got all sorts of causal landscaping going on, because you've got the futures, the past, the domains of predictability, and so on and so forth. I suggest the following assumption that there be a cut on the on scry, which has the following property: the closure of the past of this cut intersects the and contains the event horizon. So let me now tell you why I think this is a more stratified theorem, and a theorem that would, you know, cause us less hardship in understanding whether or not it represents the actual physical setup. You're interested in quantum fields. You want to know what the quantum fields are doing in this kind of space-time. With an assumption like that, that's like tailored to the properties of what happens in and around the event horizon, at least for the portion of the black hole's lifetime for which the semi-classical approximation holds, then it's a clear clear property that you can decide whether or not your quantum fields, you know, will satisfy that, or will be more likely to satisfy that, because you're looking at how these quantum fields interact within a neighborhood of the event horizon. So as opposed to having assumptions that say my future will look like this, my past will look like this, there will exist a point with this property, and so on and so forth. So although my theorem I don't think is the end game for this question, I think that a natural way to deal with your concerns is just to say, well, in the case of a theorem that doesn't have this clear stratification of robustness of assumptions, then I should just look for a better theorem. And if I can't formulate a better theorem, then that's possibly because I'm kind of, you know, barking up the wrong tree, so to speak. So what would you say to this kind of methodological kind of humility and just kind of very kind of low-level way of approaching the problem? You know, let me prove stratified theorems.
I would say that I completely endorse it. What you say is absolutely consistent, not only consistent with, but I would say supportive of exactly the kind of picture of this kind of reasoning that I'm trying to draw. So I think that your theorem is a very beautiful example of exactly the kind of thing that I'm talking about. So we have the Grotch-Kodama, the Kodama-Grotch-Wald theorem is it is problematic in many ways, in exactly the kind of ways that you're suggesting. But it was, I suspect, a springboard that you used, a way to begin your own research, and allowed you to begin thinking heuristically about, you know, what better conditions, what assumptions might be more physically perspicuous, might be more easily, one might be able to get a better grip on how warranted or not warranted they may be, how assumptions that might more easily give us insight into the physics we're interested in, you know, the behavior of quantum fields near event horizons. So I would claim that the process you're describing of how you came to prove what I think is manifestly a superior theorem to the Kodama-Grotch-Wald theorem is exactly the kind of thing that principal models support and ground. Well, that's support and ground is redundant, but you know what I mean. So, but your remark also, I think, will allow me to clarify something that I don't think I was clear enough on in the talk. Principal models are not always of necessity heuristic, rough, or imprecise. I think one can have what I'm calling a principal model that is a perfectly rigorous, precise mathematical statement that has been proven, and yet still has essentially all the properties and qualities and characteristics that I've talked about. Because, for instance, one might be able to prove a very general result about a certain kind of space-time, but one doesn't have in hand any kind of, say, existence and uniqueness theorems, or any real knowledge of the kinds of initial data that will lead to such space-times. One has characterized a class of space-times, for instance, without really knowing exactly what that class consists of. And it's that kind of epistemic looseness, even with mathematically precise statements, because The epistemic looseness comes from trying to interpret them, trying to give a real physical interpretation to the mathematically precise statements that gives the principal models their open-ended character. So I think that what you're saying, as I say, really is just more grist for my mill. So thank you.
Thank you for that beautiful answer. Jacob has a raised hand.
Thanks. Yeah, that was a wonderful talk and great discussion. In theory development historically, the community, the scientific community, the physics community comes to the end of what they trust their current theories to tell them. So one historically fruitful approach has been to combine various trustworthy principles from those theories to make general what you, I guess, would call principal models for going beyond those theories. And the hope is to find some new theory or theories in which the principal model becomes something like solution, or at least something that we can characterize more rigorously, like maybe an approximation to a tractable solution of the new theory or theories. There's a language that people have been using in the physics community lately, this distinction between radical conservatism, which is you take your current theories and you take principles that we sort of know and love, and you quote unquote push them as far as they can go. And the hope is that in this way, you'll uncover new tools, non-trivial concepts that you would not otherwise have thought of before, that wouldn't have been a continuous development from before. And a classic example is like quantum mechanics. If you just told people, several centuries ago that they needed a non-deterministic theory, they might have put something together with the probabilistic tools that they had, rather than push their models far enough and discover a completely different way of thinking about how to get stochasticity into physics. And so that other approach, has been termed by some people conservative radicalism, where you just take the tools you have and just make radical stabs in the dark. So I guess I have two questions. First, how do you think this notion of principal models fits into this dichotomy between the radical conservative approach, again, taking a bunch of principles that we know and love and just sort of pushing them and uncovering, new, potentially new phenomena that would need to be explained by theory, or discovering contradictions that you need a new theory to eliminate. And again, I guess an example of this would be, on the one hand, something like black body radiation, where here there's a prediction that a new theory has to explain the black body spectrum, versus something like the instability of the classical orbit model of the atom, where naively pushing classical electrodynamics to its breaking point leads to a paradox that a new theory would have to eliminate, versus conservative radicalism, which is take the tools we have and just sort of take stabs at possible new directions. Does the principal model picture and approach fit into the radical conservatism picture? And I guess the second question, I'm curious, like, there obviously are shortcomings, possible downsides to taking a principal model approach. What other options do you think we have, even if we, in some cases, we don't have direct empirical data, like for black hole thermodynamics, but even if we have empirical data, often it's too sparse to pin down a unique direction for theory development in advance. Like, what other options do we have? And can you think of any historical examples of major breakthroughs in theory development that didn't follow something like a principal model approach? So I guess those are my two questions, where it fits into the radical conservatism radical picture, and if there are any counterexample, if there's any reason to think that there are other approaches that could work other than principal model approaches.
Okay, good. Well, wow, those are really rich questions. Thank you. Although actually, I think that the first question you ask is more straightforward. I think that the principal model is completely agnostic between these two approaches. I think that it's consistent with both. My picture of a principal model doesn't really care what exactly the assumptions are, or what kinds of assumptions you're making, or how exactly it is you're using assumptions. The idea, the central idea of the principal model is that it by itself doesn't allow you to pick out a unique, well-defined, well-characterized class, individual system or class of systems that it applies to. And again, just to emphasize the point that I made in responding to what Martin said. These can be mathematically rigorous statements. You know, Navier-Stokes gives beautiful examples where this happens. There are known uniqueness results under certain conditions. There are known existence results under certain other conditions. But there are conditions, but it's often the case that we can either get existence or we can get uniqueness, but we can't get both, or at least not yet. And so it's not exactly clear, you know, if we just know existence and not uniqueness, it's not clear what the family of solutions is that, you know, that the conditions that we've assumed really apply to. Or all the same thing if we have uniqueness but not existence. It's not clear that any solutions exist. You know, so I would say that, yeah, the principle, the picture I'm trying to draw, I'm hoping the way I presented it didn't. My intention is that it should be agnostic between the two approaches you suggest. I don't see any reason why it should be more. It should be more easily used or more fruitful for one approach than the other. I think it should be compatible with both. On the second picture, I mean, just off the top of my head, an example where a great, I think, you know, a very profound advance was made in physics without anything like a principal model being used. I would probably say Newton's argument for universal gravity in Book 3 of the Principia. That is a case where he had a definite, really, you know, mathematically rigorously articulated framework in hand, the framework of Newtonian mechanics, the definitions and the three laws. He had a set of really, you know, concrete data models in hand, you know, the ephemerides, and he applied, you know, he constructed really precise, you know, idealized models of the planetary orbits, and in such a way that he could directly then apply his mathematical machinery to those concrete models and extract, you know, a general force law. So I think that is a case that I don't think fits this principal model picture at all.
Do you think that that's the exception that proves the rule, or do you think that, I mean, because that